Hi everyone, thanks for joining us today. I'm Cheryl Willett, BDM here at EA Technology.
And I'm Stuart Ed, head of our PD technical services team here at EA Technology.
Just before we move on, if you have any questions, please use the Q&A function in the right-hand corner of the call. We will come to them at the end. So just a little bit about EA Technology. We were founded in 1966. EA Technology has been innovating for power network operators for nearly 6 decades, recognised as a leading turnkey smart grid solutions provider, headquartered here at Capenhurst in the UK, with a global presence in USA, Australia, Singapore and China. So we have a legacy that's been created over 60 years in the electrical networks globally. Started at the Electrical Research Council in 1966. Then we transitioned into a commercial provider of technical services in 1990. Then in 1994, EA Technology was formed. From that, we have developed our technical offerings supporting LV and HV electrical networks globally, taking us to where we are today, working across multiple sectors globally. Here are just a few of the customers that we work with today, ranging from electrical network providers, data centers, water industry customers, and customers within the renewable sector globally. So today we're here to talk about the challenge facing modern electrical networks. And as you've joined today, you've probably faced some of the modern challenges of the electrical networks for different reasons, depending on your roles and interests, whether that's climate change, integration of renewable energy, aging infrastructure, electrification of transport and heating, or network congestion. One of the earliest indicators that a hidden fault is developing is partial discharge, or known as PD, and failure to detect PD can lead to catastrophic failures. On that, I'll pass you to Stuart, who can go through this in more detail.
Okay. So today we're talking about hidden problems within our medium voltage and high voltage assets. And one of the best indicators and one of the main ways that these assets can fail is through failure of the insulation material that's keeping the electricity safe inside the switchgear or electrical transformers and things like that. So it will occur in any high voltage asset where insulation is being compromised or deteriorating. The electrical discharge is a partial breakdown, so it gives us an indication that it's partially starting to break down, and hopefully if we can pick it up before it finally fails, then we can prevent these failures. What will happen is once you've got partial discharge, it will continue to deteriorate. So wherever it is within the insulating material, it will always start to continue to break down that insulation layer, and eventually will lead to failure. And different types of discharges will have different failure mechanisms and times. We also, so PD is a key indicator. So 80 to 85% of medium voltage and HV failures are related to partial discharge activity. That's what we've seen looking at failure investigations. And we've got a forensics department here in EA, and we can look through why these things fail, and also things like the DINSOPs and NEDS database back up that kind of information as well. So what is PD? So it's just, each type of PD will have a breakdown of the insulation, and it will cause different processes. So every type of partial discharge will give an emission. So we can get these emissions. We've got light, we've got heat. So light will be a little arc inside that insulating material. We've got heat, so it starts to break down and it's got some heat there, but it's not enough that a thermal camera will pick it up. It will have smell. So if you go into a substation that's got high levels of partial discharge active within there, you will get a really strong ozone type smell. So things like old paper, what photocopiers used to smell like, that type of smell, really strong ozone type smell in the substation. If that's the case, you might want to just turn around and leave that substation, because it's probably in a really bad condition. Sound as well, so there's you can hear PD, so you hear that crackling type sound from partial discharge. And the final one is electromagnetic waves. So in our instruments, we develop sensors to detect these types, and the different types of partial discharge, going to on the next slide, create different types of emissions, and stronger in different ones. So we'll go through that a bit more on the next slide. So we have internal partial discharge. So an internal partial discharge is a void within your insulation. So you've got a HV conductor, you have something around it like rubber or EPRs, cast resins in transformers and bushings and things like that. Cable terminations will have XLP type cables. If you've got a little air pocket within there, that's got a completely different dielectric strength to the material around it. So whether that's resin or anything like that, would be a lot stronger. So you start getting these little high electrical stress in the air pockets, and they discharge then. So every cycle we're getting a little discharge within this air pocket, and that will cause partial discharge, and the emission, the actual void, will microscopically be getting bigger every time that happens, and it will lead to failure over time. So we can trend that over time. If you think about that and how we're going to detect it, we think about the emissions that were on there, the last slide. If inside that air pocket there will be a little bit of there'll be a sound, you'll hear that arc. You'll have the light. You would have the different emissions. But ultimately, we can't pick that up with a sensor while it's in normal operating condition, because that's all kept within that void. So the only realistic way that you're going to be able to detect an internal partial discharge outside, non-intrusively, while it's in normal operating condition, is going to be through the electromagnetic waves that are created by that partial discharge event. So for that type of partial discharge, the primary way of detecting it, or the only real easy way, is to detect it through either transient earth voltages. So we pick those up with our sensor, capacitive coupler on the outside, or things like HFCTs or UHF type sensors as well. So they're for the internal partial discharges. The next type of discharge that we have is surface partial discharge. So we've got a tracking across the outer surface of the insulation. So you see this quite often in cable terminations, if the cables are too close together. Also where the cables go too near, they could be a bit too close to the earth metalwork within a compartment. Also bushings, bus bars where they go through from panel to panel. You start getting this surface tracking. You'll see something on the outside of that insulation. And again, if we think back to those emissions, we will get light. So you would see little arcs going across the surface. You would be able to hear it, and you'll be able to smell it and things like that. So you will get electromagnetic waves, but they're quite weak for the surface discharge. The amount of energy in each discharge is quite low. So although electromagnetic waves will be there, they might not be as easy to detect in normal operating conditions. So for the surface discharge, we do try to focus on the sound, because although there is the light, again, that we talked about, unless you can see inside the area where it's being done while it's in normal operating condition, it's quite difficult. So we generally focus on the sound. We can hear that crackling type sound through a vent or through a contact probe. Then the final one is corona partial discharge. That's something that's just too sharp. It's got too pointy at the end, and basically it will not be able to control its electrical stress in that area. You hear it a lot on overhead lines on a rainy day. It's been a couple of weeks since we've had a rainy day in the UK now. But you do, if you hear them overhead lines cracking, that's probably not too much of a problem. But if you've got something that's been cut too sharp within a switchgear panel, it will create ozone and the acids and stuff within that panel, which will lead to surface-related partial discharge as well. So again, the best sensor type for that is, again, going to be ultrasonic, because that's going to be the most sound. Again, corona can create quite strong electromagnetic waves as well. And there's a few intermediate partial discharges, things like gap discharges and things like that we can see in the field as well. But these are the three primary types that we're focused on while we're testing with our instruments. And ultimately, these will lead to progressive failure of discharge. So we want to be detecting partial discharge in our surveys and in our switchgear types. And we're just going to try and prevent these unexpected asset failures, so that hopefully we can increase the safety. You know, we're all working in these substations on a regular basis. We want to hope that we're as safe as we possibly can. It's never a completely safe environment, but at least if we can go in with our taking partial discharge measurements, we can make ourselves feel a little bit safer in there. And ultimately, we can save some money as well if we prevent a costly failure, downtime, and we can plan our asset replacement as well. So if we trend our PD activity, or we put things like monitors and stuff that we'll talk about in the next section, we can extend asset life if we're monitoring it, and we can also pick up things that prevent those failures and costly repairs and things like that. So early detection will enable intervention before any minor defects become major failures, and you end up with a circuit breaker that looks like this on the picture. And I'll pass back over to Cheryl.
So here at EA Technology, we've got two main monitoring solutions for detecting partial discharge. We have our handheld instruments, which is for periodic condition assessments, ideal for routine inspections, lower initial investment. And the portable equipment, it can be used across multiple sites, so it's a lot more versatile when people are on sites doing these monthly or 6 monthly checks, and whichever that they prefer to do on their maintenance schedule. We then have our permanent monitoring. So the permanent monitoring is continuous 24/7 monitoring, ideal for critical assets because it gives immediate detection of developing faults, and it provides trend data for early warnings of faults that are coming. So just a bit more information on the handheld PD detection, what we've got. This is our UTP2 Plus. Its handheld monitoring provides a practical and cost-effective approach to condition assessment, allowing the engineers to quickly evaluate asset health during the routine inspections. The portability of the equipment enables large numbers of the assets to be surveyed efficiently, helping to identify developing faults before they become that critical. The benefits of having the handheld is that it's a lower cost, it's got fast asset screening, it's portable, flexible, like I say, you can take it around multiple sites. You get immediate results on for the partial discharge, and it's best for surveying large asset populations. Moving on to the what data captures on it. So a key advantage of the UltraTED Plus 2 is the ability to verify and assess the partial discharge activity immediately. So detailed, you get the phase resolved partial discharge plots, which are available on the instrument, helping to distinguish between different PD sources, and you'll see that on the screen there available. This is what you will hear on this when you're listening in through the ultrasonic on the partial discharge. So you'll hear that crackling noise, and that's what you'll be listening out to. Okay, so moving on to the continuous PD monitoring. 24/7 monitoring captures intermittent PD activity, and it provides real-time alarms, best for critical or high-risk assets. The recommended approach for it is using the handheld monitor on the screen and prioritizing assets, then deploy monitoring or continuous monitoring on critical assets where ongoing surveillance is required. So there's a difference of different benefits for both ways of measuring partial discharge. So the continuous monitoring provides continuous visibility of the asset health, enabling earlier intervention, reduce risk, and improve reliability for the critical assets. And like I say, the benefits for both based on what the recommendation is for your site and the portability of what is required. I'll pass you back to Stuart now, who's going to go through some of the case studies we have using both of these approaches.
Okay, so I've got a number of case studies here today, just to show you different ways of approaching things. So the first few will be related to handheld surveys. So obviously, we as a team, we go out every day, pretty much doing PD surveys at different customer sites, and they are quite often done annually or every 6 months, depending on the asset type, and that is gives you the benefit of being able to do quite a lot of assets with just one handheld product. So in this case here, we've done a partial discharge survey at a site, and it's the first time we've ever been to this particular site when we did this PD survey, and we can see we picked up some high level surface related partial discharge, and I'll play the sound file for you. So so in that case, we've been there and we've done that PD survey and we've picked it up with a handheld device. I think the thing that we can think though is also we were a little bit lucky. We were lucky that we got there at that particular time. We have monitored things like this type of failure, surface related partial discharge. So we can see in the picture on the right, we've got surface tracking, the actual the bushing between the two live conductors is getting a considerable track across there. And you look at that picture, we must be looking at months at the most that could have carried on discharging like that. And we have in the past seen monitoring cases where we've actually monitored something from not detectable to failure within sort of 3-4 months. So the fact that we've done this PD survey and we've picked it up in this occasion is maybe partly lucky rather than well planned as such. And then we've got to act on it as quick as we can when we find this, and it's quite considerable amount of damage and repair related to that as well. So in that case, we could miss it. And I'll show you. So we'll just do another case study. The next one is some transformer cable termination boxes. Again, we've picked it up with a surface related partial discharge, and we can hear it. Again, I'll play that for you. It's a bit not quite as distinct as that one. This was detect. This is actually detected with a contact probe in the field. So if you know, there's 2 types of ultrasonic sensors. So you can have an ultrasonic airborne sensor where you're listening around the gaps. In this case, it's obviously well sealed. It's an outdoor transformer cable termination box. So in that case, you haven't got an air pocket to listen to with your ultrasonic microphone. So like the previous case, we actually listened through the vents on the cable box and picked up that sound very easily. In this case, we couldn't do that. So we've applied the contact probe. So the sound is not quite as distinctive, but we did manage to pick it up. We can see it's got quite advanced by that point. Also, there's things like the Ultra Bolt now that we've recently released, which we could fit into things like cable termination boxes, and where it hasn't got an air vent, and it gives you a much better path inside that cable termination box as well. But again, we've managed to pick it up. We've prevented the failure, but again, it's quite close to failure by the time we've managed to pick that up with our annual surveys. And then this next one is a case where we've been trending a transient earth voltage measurement. So transient earth voltage, mentioned earlier, is related to internal partial discharge. So we're expecting to see an ultrasonic, an internal void within some insulating material that's in this area of the switchgear. So each year we go to this particular site and we carry out a partial discharge survey. And we can see that in October 23, we've seen this cluster. October 24, it's built up a little bit more. So we've gone from sort of about 18 dB to sort of 20, 21 dB in 12 months. And then I'll show you the next one on the next slide. So again, this year we've gone back and we've picked it up, and it's now gone to just mid 20. So we're still, if we're on our instrument, we're still in the amber range, and we're able to trend that over time using a handheld survey. So in this case, handheld is probably just as good. You can go there once a year and you pick up and you can trend the activity over time. Whereas the first two cases, I'd say we were a bit more lucky that you've been at the time you've been and you picked it up before the failure. So that's where we're trying to compare the difference between putting a monitor system in. If you put a monitor system, you know from day one when that partial discharge is starting, and you can plan your actions a lot longer ahead of time. But also, obviously, there's a lot of cost involved in that. So it's getting that balance of whether you need permanent monitoring in the assets or not. So I've got a few case studies now where it demonstrates how permanent monitoring can pick up these things straight away, and we can act on them as quickly as possible in that case. So this one here is a substation, and we were putting a monitor in mainly for it was trend. We're watching high level transient earth voltage activity within CTs within this substation actually, and that's why the system was there. But whilst obviously you're putting a system in, we've got VTs that are mounted on the top of the switchboard, so they're mounted the horizontal, the rack in, and they give us our voltage, our low voltages inside the substation. So in this case, we put some ultrasonic microphones pointing at the VT as well. And the system had been running for a couple of years, 20 months actually, before this happened. And then one day, there was a significant increase in the sound coming from this particular VT here. The PD type sound increased. Our algorithm can tell us that we think it sounds like partial discharge as well with the monitoring system. So at that point, we can then speak to the local staff and ask them to go down to the substation and carry out an investigation. So at this point, we've picked it up on the very first day, and it's been running for about 2 weeks. And they can plan their outage, they can plan their what the next steps are on this. They took it out, and you can see in the top corner here some significant burning and tracking on there. So I don't think this would have lasted very long. So if we go back to thinking about how we could, if we were doing a handheld survey, if we were doing one every year, you've probably got 1 in 4, 1 in 5 chance of catching that on your handheld survey. If you'd just gone and done a handheld survey every year, if you went the week, if you went in the week before this, you won't pick anything up, and you won't be coming back then for another year. So then you think, well, maybe we need to do our handheld surveys a bit more often. So we could go every 6 months. So you got twice as good a chance of picking up at that time. If to get even better, you might want to do it every 3 months. And then that's when the balance between the monitoring, permanent monitor solution and the handheld solution starts to line up, because you're using a lot of time, a lot of man hours to do these surveys each time. And the more you do, the more you're doing to prevent the failure, the more cost it actually inherits as well. So then you can get to the stage where permanent monitoring is actually a good financial decision. And then this is another case of this particular one. They had high level, they put a new cable termination box in and decided to monitor it from day one. And within the 4 months, this PD source started to emerge. So we started to see this void within this. They put like a compound, a G38 compound into that cable termination box. But if you haven't got it in quite right, and you've got any little air pockets within there, at first it might seem fine, but then as time goes on, you'll start to see these activities, and you can see there's probably multiple air pockets, because if you look at this actual phase resolve pattern, we're getting different lines and different areas. So that could indicate that there's different little air pockets within that insulation. And again, we've been able to monitor it from straight away, so we can see it rise up over time. We know there's something not quite right with how that's been done, and we can again start to plan our intervention within a timely manner and not straight away. Whereas if you do handheld survey, you go there and it's like that, you don't know if it's been like that for a week or if it's been like that for 5 years with the transient earth voltages. And then this is another one. This is actually a bit of a strange one. It causes partial discharge when a actual fuse blows within a VT. So high voltage VT, the big ones have these fuses within them, and if the actual fuse itself blows, it will then you've got a separation. Then you can start to get actual tracking across the fuse, because the line is the path it normally uses right through the middle of the fuse is no longer there. It tries to go around the outside, and you start getting tracking on the outside of that, and that causes really high partial discharge type patterns. And this is a case of that here, where we're monitoring, and we're actually monitoring a substation a few hundred meters away that was feeding this substation, and that was picked up on all the cables, because our cable monitor was on all the cables in the other substation, and it picked up the high levels of partial discharge activity. Again, we've seen it straight away. We can go and replace that fuse as quickly as possible, so it doesn't eventually track across the outside and lead to a failure. So I'd say the advantage of the monitoring, we know from day one that fuse has failed. Okay.
Thanks, Stuart. So just to reiterate that we do have the Q&A function in the top right-hand corner of the call. There's also the QR codes that is on there. So if you do want to pop any questions, you can do that. But I'll just leave that on so everybody gets a chance to go on to the Q&A for a minute, and then we can do that at the end of the presentation.
Right, okay, so we've got a question regarding detecting internal partial discharge in a distribution transformer. So I'm assuming this is an oil-filled distribution transformer. So if you've got internal partial discharge within a oil-filled asset and also oil-filled distribution transformer, then the most sensitive way is oil. So you do oil analysis. If you've got it within we have seen cases where we take TEV off the cable terminate, off the cables as well, and we do see high levels of TEV. But that has normally been a follow-up from a already known high levels of dissolved gas analysis through the oil of that transformer. So that's a primary way of detecting it in that. If we're going to cast resin type transformers, you're probably better trying to get HFCTs on your actual cables connected into the transformer. And also we've done some stuff around UHF, but UHF has got to be within the actual compartment itself. So you need to try and put a UHF sensor behind the steel, because the problem with the actual box that the cast resin transformers are in will block the UHF signal itself. So you do need to be inside of that point to become a bit more of an intrusive testing within that case. So thank you for your question. Another question: does PD occur on low voltage LV transformer box? No, not really. You need over 1,000 volts of electrical stress to get partial discharge. So generally, 3.3 kV assets has just over 1,000 volts of sort of phase to ground stress. So we quite rarely on that type of asset, but then anything above that, you can get partial discharge. LV transformer cable box, you might hear some arcing inside there if you've got bad connection or something like that. And the only other case of that is if it's at high altitude. So things like planes, they might have a 240 volt transformer on them, and they can still get partial discharge to that because of the altitude in that case, but not in normal situation. Any other questions? Yes. So and Hi, is an annual PD recommended on 11 kV switchgear, which we normally see in the UK? What areas and what is best tech would be best suited? So yeah, so 11 kV switchgear is a very, very common PD survey that we do. So we do PD surveys of that type of asset weekly, in a lot of industrial sites, a lot of I know a lot of distribution companies in the UK do a lot of PD as well on that level. So 11 kV is definitely one to do. You need to understand the switchgear makeup. So when you're looking at your switchgear panel, you need to understand where the critical components of it are. So older type of switchgear where you had things like say Rayroll like VMX and Rayroll LMT and things, they had a separate circuit breaker that actually racked up and racked down. And in those types of setups, you want to really focus on obviously the circuit breaker, where the interaction is, where the bushings plug in and out, things like that. You've also, the most common area of problems is cable termination boxes. So you certainly need to be doing a survey of the cable termination box using both transient earth voltage and ultrasonic accessories. And then obviously the bus bars and any airfield component should have a survey of that. So when you're doing a survey of it, and then the more modern type of equipment where it's fixed pattern, again, you need to just have an idea in your mind of where all those parts are. Google's quite good these days. You can put in the name of the switchgear type and it'll come up with quite often a little picture of what it looks like inside. So you can think, well, that's where all the cables are in this one. If some cables now are at the front, some are at the back. So the main thing is just to know where all your components are and do the appropriate measurement technique for that type of switchgear. If you want to get in touch with us, we can tell you, we can set up, when people get the equipment, they tend to have a training course and we'll show them, and we can go attend site, do things like benchmark surveys. We can set it up so that it's all in our managed survey platform. So the next year you'll be able to do repeats exactly the same as what our team did as part of your benchmark surveys. That's a really good way of getting to understand the best things for your particular assets and switchgear type, because we have seen most of the switchgear types at some point in the when talking about the smell of PD, it means smell of ozone. Yes, it's sort of an ozone type smell. So it smells a bit like chlorine and things like that. That type of smell. So it's very distinctive. If you walk into a substation and it doesn't smell of sort of bit of old oil or something like that, then there's something. Yeah, that's probably that type of smell. So it is quite distinctive if you go in there and smell that type of thing. Given modern cable installation system manufacturing technologies that maximize void formation, is partial discharge. Yes, so obviously the more modern cable types, you've got XLP and EPR type installation. As you say, they will be tested in the factory to a very low, very, very, very tolerant. So that piece of cable between the two substations and between any splices is probably really reliable, and it will also fail in a very short space of time if you did have a problem in that area. So if you did have PD electrical tree or something within your XLP installation, then it will most likely fail very, very, very quickly. So PD testing again becomes a bit more difficult at that stage. But when you go to the joints and the terminations of these systems, they are still done in a substation, in a joint pit on the road, and things like that. They have a bit more tolerance, they're a bit bigger, they have a bit more stress control, but they're the areas that you're most likely to find problems. So if you've got a 1,000-meter cable and it's got 2-3 joints in it, then yes, certainly it needs to be tested for partial discharge to ensure there's no problems in those joint areas. And the main bits in between are unlikely to have any partial discharge, but the joints and terminations are the key area for those types of systems. Are they shielded against magnetic fields or sources of interference? No, there's no real shielding particularly. obviously we're picking up in certain frequency ranges, certain frequency areas. We have things like algorithms that can detect the types of partial discharge, and we can identify what things like variable speed drives, inverters, stuff like that. We can identify the different types of those, so we can separate those out. We do have TF mapping in a post survey analysis step as well. So there is a number of different ways of getting that. These days, you don't see a lot of interference in the substation. You know, when you're doing a survey, majority of this, you know, we do surveys in substations all year round, and the amount that interference interferes with the result is very, very few. At that point, you can install things like monitor systems that do have more discrimination, so they can have time of flight and things like that between the aerials. So our monitor system has aerials that go in the corner of the substation that will have time of flight between that, so discount the interference in that way. Cases presented. Do you have detection cases for high voltage assets? Yeah, so most of the ones that we talked about there were 11 and 33 kV asset types. But yeah, we do partial discharge testing right up to higher voltages. We've recently done a project at 275 kV. We were doing cable sealing ends and what they call surge arresters and things like that. So we have got stuff like that as well. But most of our work, you know, to be honest, most of our general day-to-day work is in the medium voltage 1133 kV type of equipment. No problem. Yeah. So we do have is our portable detector applicable to GIS switchgear? Yes. Again, we do have other sensor types. So we have the band joint sensor, so that can be put onto the bands between each GIS cubicle. So when we talk about GIS here, I am referring to the tubular GIS above sort of 132 kind of voltages. So that will pick up PD from that. Also, HFCTs can be used on that type of equipment as well. But generally would be the UHF band joint sensor for that. That type of equipment sometimes come with built-in sensors, and again, the Ultra Plus 2 can be connected to that as well, to those as well. Do you want to leave our TEV detector does have, so do you plan to develop TEV detector with 2 or more channel sensors? Like we do have we do have a second TEV sensor for the Ultra Plus 2, so it has the locator probe as well, so you can do time of flight between the two TEV detection with the Ultra Plus 2 as well. So we do have that. Is a flashover between transformer LV busbar and the box metal enclosure related to PD? Most likely not. No, it's probably just due to too smaller clearances, because at that voltage you would have to be quite small clearance, but it's most likely just due to a clearance issue or something like that. It won't be partial discharge related. So can you estimate end of life remain asset and can it be reversed in any way? Or to plan replacement, and is it truly non-intrusive, or would they need to power down? So all the measurement techniques that we've used here are so TEV and ultrasonic is completely non-intrusive, really. HFCTs, it's a bit of both. It depends if you can physically install those under normal operating conditions, so you might need to power down for that. But yeah, transient earth voltage and ultrasonic is generally completely non-intrusive. Regarding remaining asset life, obviously, if we pick up a PD, then we will generally recommend retest periods at that point. It can't really be reversed as such, but things like things that can affect partial discharge or create partial discharges, things like humidity and things in a substation. So if we pick something up and you can really improve the environment in the substation, you can certainly extend your asset life at that point on those types of things. Obviously, the other type of, if you pick up an internal void, there's no way of really reversing an internal void. You'd have to replace that particular component that's got the void within it. Yeah, so this is so I've got somebody who's a SAP for an IDNO, often switches over customers' electrical equipment. It's similar to us, we don't switch over people's equipment, but we're certainly around when people are switching things. So yeah, I know what you mean. And like, as you say, some customers are better at their substation inspections than others. So would a portable tester before switching prevent potential flashover and failure of the equipment? Or is it more of a detecting a fault within the equipment that is brewing? So yeah, certainly we would definitely recommend that you are doing a partial discharge survey of any switch you're just about to operate. If you've got a high level of partial discharge, particularly again the surface PD, if you're going to be racking down an old circuit breaker, you don't want to be doing that if you've got high levels of ultrasonic activity coming out of the spouts area, for instance. So it certainly will help you keep yourself safer, I would feel. So we certainly recommend that you do that before any kind of switching operations. Yeah.
We're just going to move on now from the questions, and any that we haven't answered, we will send you an answer across, just that we're running out of time. So if you want access, everyone will receive a video of the recording, but if you want access to the slides, if you scan this QR code and pop in your details, that way you'll receive it in due course. I'll just leave that on for a little second just so that you can scan the QR code and get the details and get the slides quicker. And finally, we've just announced our industrial forum again for 2026. To register, please use this QR code, so just this one on the slide, and come and join us in October in Birmingham. Anyone that wants to exhibit at the industrial forum or a sponsor of the event, please just reach out to myself and we can arrange this. I must stress there are limited spaces around this, so if you can be quick, if you do want to sponsor it or you would like to exhibit or be even a speaker at it, just reach out to us and we can get that arranged as quickly as possible. I'll just leave this on as well, but registration is free, so if you could just register your interest here and then we'll follow it up in due course. So any questions that we have and gone over today, we will capture and we will get back in contact with you. If you have filled out any details or questions that you've put on through the website, they'll also be answered. So it's just to say thank you for joining us today. And I hope you find it useful. And if there is anything, please reach out to us. My name is Cheryl Willett.
And my name's Stuart.
Thanks so much for your time. Thank you.